Okay, so this is something called the Kepler's law. Kepler's law of planetary motion. Motion. Okay, so now this is the last thing, and this is the most asked thing. Okay. So you should know the derivation, the calculation, and the theory as well. Okay. So planetary motion is basically when you have, let's say, so first write the laws that we have. Okay. The first is um, um, all the planets perform circular motion, motion around the planet, around the star, sorry, sorry, around the sun. Okay, this is the first thing, right? And sun is the center of rotation. Okay, and the paths are circular. Okay, or we don't have to write this one. Okay, so the first thing, actually, in reality, the path is not a complete circle. It's somewhat elliptical, but we assume that like all the planet perform the circular motion around the sun. Okay, so this is the first thing we have, right? Now, the second rule is quite difficult and it's not a part of syllabus. And the third, talking about the third rule, it's basically says that the period of the period of the satellite satellite around the mass is given by t square is k times r cube. Okay, and okay, so these are the two laws that we have, and for the second law, we have to do the workings. Okay, but let's talk about the satellite and the motion. Okay, so first of all, okay, So satellite is basically it is basically of two type. Okay, it can either be artificial, artificial, or it can be natural. Okay, artificial or natural. Okay, so so the artificial satellites are okay. So the artificial satellites are basically those that we launched in this space. Okay, and the natural satellites are those that is basically there in this space orbiting any specific planet like moon for us, right, is a natural satellite. Okay, so and this type of circular motion is called the periodic motion. Okay, so the planetary motion, this planetary motion is known as periodic motion. Okay, and periodic motion is basically a motion where we have the where the object repeats itself after a specific amount of time. Okay, so planetary motion is known as periodic motion. Okay, and the periodic motion is motion that repeat itself after specific period. Okay, so now if we try to understand the planetary motion, so so this is the concept of the planetary motion that we have. Okay, where I have the satellite and I have like the natural satellite and the artificial satellite, and both are orbiting the sun, orbiting the Earth. Okay, at a specific height, right? And if we try to find out the if we try to find out their motion, okay, and their time periods, so for that we have to use the Kepler's third law, and for the Kepler's third law we say that gravitational force provides centripetal force to the object. Okay, so whenever you are driving this equation, t square is directly proportional to k times r cube, you always have to write this statement in the beginning. Okay, and then you can say that the gravitational force Fg is basically gmm over r squared, and Fc, which is the centripetal force, is mr omega squared. Okay, omega squared. Okay, you can also take mv square over r, but for now we are talking about like we are relating the time and the radius or the separation, so that's why I'm taking r omega square and not this one, right? Now Actually, the distance between the two, the distance r is basically the separation from the center till the end. Okay, so this is your r. Okay, this is your r. Okay, this is r is basically the center to center separation, right? Now we can carry on the derivation. We can say that fg or gmm. Sorry, we can say that fg is equals to mr omega squared. Okay. And then, because this is the only force providing the resultant force, Fc is the resultant force, right? And according to Newton's third law, according to Newton's second law, where you say F equals to ma. So in place of F, I write this one, and in place of ma, I wrote this whole thing, right? So, and then I can replace Fg with gmm over r squared equals mr omega squared, right? But please keep in mind, guys, don't write Fg equals to Fc, okay? This is an incorrect physics, okay? Although mathematically it is the same thing, but according to physics, it's not the same thing, right? So if you write this one, then this means that Fg is a separate force and Fc is a separate force, right? And both are the different type of force, and both are acting on the same object, right? And they are equal and opposite, right? So this is what this equation means, okay? But this equation means that Fg is actually the only force acting on the system which is unbalanced, okay? And due to the unbalanced force, it accelerates the system, okay? So I explained both the I explained the physics for both of the equations, okay? Now, um, coming back to the equation, so it becomes Gm equals to r cube omega squared, okay? Then you can expand omega. We know that omega is equals to 2 pi over t, 2 pi over t, okay? This is an incorrect physics, by the way. And then solving this thing, Gm is equals to r cube and then 2 pi square over t, okay? Now, so if we solve it further, so I'll get t square right here equals 4 pi square over Gm and then r cube, okay? So this is a law that we will going to use, and over here, 4 pi square over gm are the constants, right? And yep, this is the derivation, by the way, and this is frequently asked question, okay? So you should remember it, okay? And if you try to make the graph for it, let's say we have t square and t square and r cube, okay? So the graph will be a straight line passing through the origin, okay? Passing through the origin, where gradient gives you the 4 pi square over gm, right? So if they ask you to find the mass of the Earth or the mass of the planet, and they've given you this graph, so you can find out the gradient and then you can manipulate for m, and you can solve, right? And if they reverse the axis like this one, where you have, let's say, r cubed here and t square here. So the graph will again be straight line, but this time the gradient will be the different. Okay, this time the gradient will be gm over 4 pi square. Okay. So these are the two cases, right? Now, this is one type of the question that they can ask you. Okay. And you can, by the way, relate the two values of t for one planet. Okay. Um, so if you have for multiple satellite of the same planet, you can relate t1 square over r1 cube is equals to t2 squared over r2 cube. Okay. So this is for the two planets or the two satellites, but the condition is they should be of the same planet. Okay. Don't, not for the different planet. Okay. Now, if we okay, let's just solve for let's say moon and for a satellite called the geostationary satellite. Okay. So I have the moon. Okay, a moon in the Earth system. So if you consider the moon and the Earth system, okay, so moon and Earth system. So let's imagine that like we have the Earth and we have
So
the moon. Yes.
can you scroll a bit up? I just want to see the.
Mm-hmm.
No, a bit down. The
This one.
multiple satellites that formula. Yeah.
Yeah. Okay. So the moon and the Earth system, and we have the separation between
Okay.
the moon and the Earth is let's say r. Okay. Now the moon has a mass of okay. The Earth has a mass of um 6.0 exponent 24 kgs. Okay, this is the mass of the Earth, and for the moon, for the moon, I have 7.4 exponent 22 kgs. Okay, and the separation between them is like r is the separation. Okay, and that is 3.84 exponent 8 meters. Okay, you have to use the equation and you have to find out the the time period required for the moon to complete one of its orbit around the earth. Okay, so you have to use t square is equals to 4 pi square over gm, right, times r cube. Okay, and find find the period of the moon. Okay, just try it, please. Uh, Always keep in mind that whatever the center mass is, you have to use the mass always. Okay, you have to use its mass always. Okay, so this is in this system, the Earth is a centered. Okay, is a center of the like Earth mass, Earth and Moon. This is Earth and Moon system, right? So you have to use Earth's mass, right, for this calculation, right? Clear?
Yeah.
Just put in the values and solve. Done. Yes, guys, done. Acha, kindly convert it into the days, okay? Okay, let's try together. Okay, so in place of t square, okay, 4 pi squared remains the same, and you have to take g, which is 6.67 exponent negative 11, okay, and then mass of the earth is 6.0 exponent 24, okay. Always consider the mass of don't consider the mass of the satellite for this one, okay. Just consider the mass of the object around which the things or the satellites are moving, right? And times by r cube, so r is 3.8484 exponent 8 and cubed it, right? And then just square the whole answer. Just square root the whole thing. Okay.
I'm getting
Hmm.
2.4 into 10 to the power 6
Okay.
as
So
cubed.
2.4 exponent 6. Okay. S. Okay. So if we try to convert that into the days, okay. So divide by 24 and divided by 60 and 60, right? So just convert that into the days, please.
27.4.
Perfect. So basically, this is how much time the moon take to complete one of its orbit. Okay, 27.4 days. Right? Now, if you imagine the system, the Earth, a mass system, the Earth and the Sun system. Okay, so Earth and Sun system. Okay, now we know that the Earth take 365 days to complete one of its orbit around the Sun, right? Which is 1 year, right? And let's try to find out the separation between the Earth and the Moon. Okay, while the mass of the Earth, so in this case, the mass of the Earth is 6.00 exponent 24, and the Sun is 1.99. Okay, or just take 2.00 exponent 30 kgs, and you have to find r. Okay, separation. Okay, and just keep in mind this is the Sun and this is the Earth. Okay, this is the Earth. This is the Moon. Okay, just find that out, please. You have to use a similar thing. We are finding the find the
Sir, go up for a bit.
just a minute, please. Find the separation between the Earth and Sun. Yes.
Is this like a frequently asked question?
Yes. A lot of time.
Okay.
Mm, okay.
1.6 times 10 to the power 14.
Or it should be 15, not 14. Okay. Irfan, what about you? Let's try together. Yes. Irfan, what about you?
I'm still doing 1 second.
Okay. You first have to make R the subject, right? So RQ is equals to T squared then GM over 4 pi. That which mass you used?
Huh?
The sun.
The
The
sun's
sun.
mass. Yes. Okay, good. So we know that the Earth and the Sun required 365 days. So 365 days, one day contain 24 hour, 1 hour contain 60 minute, 1 minute contains 60 second, and we have to square it. Okay, then we have the G value, which is 6.67.
See.
Yes, negative
No, we
11.
have to multiply 12 months as well.
Uh, don't do that. Well, they discourage multiplying the months when you while you're converting into air or air into second. Okay, so don't do that with it. Okay. Okay, so this is it, and then we have the mass of the sun as 2 exponent 30, and then divided by 4 pi r squared, and then you have to cube root the whole thing. Okay, this gives you your r. Okay, how much?
5.8 to the power 16.
Okay,
5.8 times 10 to the power 16.
we have to cube root it, not square root. Okay, so I am getting the r cube as um 3.36 exponent 33. Okay, and if I cube root the answer, so I'm getting 1.497. Um, Meghdad, are you getting
Yeah.
1.497 exponent negative 11 meters? Okay, it was also not negative 15, it was 11. Okay, 1.5 exponent. Okay, is that clear, guys?
Sir, negative
Yes,
11.
not negative, it's just 11.
Oh, it looks like there's a negative.
Right. Yep, sorry.
Yeah, I got this from you.
Perfect. Okay, now, so these are two systems, right? Now you can consider one more system, which is what we say is as the geostationary satellite. Okay, so let's talk about it first. Okay, they ask you a lot of time about it. So okay, geostationary satellite. Right. Okay. So it is basically a satellite used for GPS. Okay. Global positioning system. Okay, and it has three properties. Okay, one, it always remain above the equator. Okay, above the equator, right? And the second thing is it move from west to east. Okay, and the third thing is period of its rotation is 24 hours or 1 day. Okay, so if somebody is living up at the equator, and if let's say the satellite is visible with your house or with your home, right? So for like 24 hour in a day, you will see the satellite right above your head. Okay, and it seems like it's not moving, right? But it is basically moving with the position or with the movement of the earth. So that's why it looks like stationary. So that's why we say the geostationary satellite. Okay, now, so if you see, so this is the earth I have. This is the earth I have, let's say. Okay, and this is the axis. You know that the earth is tilted around its own axis. Okay, so this is, let's say, the axis. Okay, this is the axis, let's say. Okay, and I want to know that, let's say, this is the satellite. Wait.
So what was the last point?
The period of the period of its rotation is 1 day.
Okay.
Okay, so come on. And the wings I have, and the wings I have for the satellite. Okay, okay, okay. Right. So let's say this is the satellite. Okay, and this is moving around the square. Look, it's looking quite fine. Now it's moving around the sun. It's moving around the Earth. Can you guys determine its period? Its separation? Yes. Can you guys determine separation, please? Let's say it is moving like that. Okay, with this being the center. Okay, yes. So I just want to know the separation. Okay. Yes. What will you do?
Uh, can we do the same thing as the last one, the last one's formula? T
Yes,
square.
yes, you have to use the same formula. Okay. But yes.
You take the Earth's mass because it's rotating around the.
Yes, 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 it's very good.
So
Basically, if I put in the values, so the Earth has a mass of 6.0 exponent 24 kgs, okay? And you know its time period, you have to find the separation, okay?
Okay.
So, and you have to use a similar formula. The formula is t squared is equals to 4 pi square over gm times r cube, right? Okay, let me just find one more thing, one more type of question for you guys. Do you guys know the values? I'm just scrolling down for. Okay, sure then. Venus and Neptune. Okay, let me. Okay, copy and paste. So let's say I have the sun. Okay, okay, this is the sun. Let's say, and two of its planet. Okay, one is. I'm just making another question. So okay, they
For
and
this one, I got the answer.
mhm.
4.23 into 10 to the power 7.
Okay, I mean that's what you are getting.
Same answer.
Same. Okay, fine. Or like that. Okay. Now, so okay, consider this one. Okay. So let's say we have the sun. Okay. We have the sun with us. Okay. And wait, the sun and one planet is Venus. Okay. This is Venus, and that is Neptune. Okay. Okay. So you have to use the similar formula that we were using to find out the period of the Neptune around the sun. We don't know anything. Okay. Um, so this is sun. Okay. Okay. Now,
Wait, so what are we supposed to find?
the time period of the Neptune. Okay.
So do we have to like add up the distances of Venus
No,
and
no,
Neptune
no,
from
no,
the
no.
sun?
No, obviously not.
No. Oh,
You
I
have
didn't see
to
the.
you have to use this one, no? When you have the multiple satellite around the same planet, we have to use this formula, okay?
Okay.
So
Is it T1 squared
yes,
or R1 cubed?
you can see the actual formula. So the actual formula contain t squared and r cubed, right? So they remain square and cube, but they just get one and two, okay, in their subscript. Yes, guys, done. So you just need to do. Let me just solve for you. So for T1, I am considering 0.615, okay, and
Into
just
24
yes into 24.
into 60 into 60.
Yes, and you have to
Five
square it.
3.
So wait, wait, don't find the individual answer. It will make more difficulty in your calculation. Okay, and then you have 1.08 exponent 11, okay, because it is powered 8 and then kilometer, okay, is equals to the t squared is what we are working for. And if you multiply that by r cube, okay, so you'll get what you were finding, okay. So the other value is 45 exponent 11 and then cubed, okay, okay, and whatever the answer, you just need to root it.
So how 11 cubed or 8 and
Bro,
cubed?
no, no, no. It is 8 and then kilometer. So I convert kilometer into meter by increasing the power to 3 and then I cubed it. Okay, clear? Okay, let me just do the working for this one.
I'm getting
Mm-hmm.
1.43 into 10 to the power 7.
1 point. Okay, let me also try. So 45, 45 exponent 11 and it is cubed. Then 0.615 into 24 into 60 into 60 and squared. Okay, and then 1.08 exponent 11 and it is cubed. Okay, yes, I'm getting the same 1.4 exponent 6. Okay, so 1.43 exponent 6. But if they ask you to convert it into year, so you just do 24 into 60 into 60, right? So I'm getting 165. Clear? Which means 165 year. Okay, So 165. So Neptune required 165 years to complete one of its rotational motion, okay, around the sun, right? Which mean the Earth will rotate for like more than 1.5 centuries, and after that, the Neptune complete one of its motion. Okay, is that clear, guys?
Yes.
So now I'm stopping the class right here. We completed the chapter. I have one more thing to tell you. We'll discuss that in tomorrow's class. Okay, it's not it is asked sometime, but it's not that much common. But we'll do tomorrow, and then we'll do the pass question. Okay, in tomorrow's class as well. Okay, and yes, the rest of the things are like done. And after that, I'll give you the homework. Okay.
Wait, sir.
Yes.
The
Mm-hmm.
T is equals to 165.
165 here. Yes, I'm getting
Oh, you're
165.
converting into year. Okay.
Yes, this is years. Okay, and this is seconds. Right? Clear? Okay. So
Yeah.
that's it for today, guys. Inshallah, meet you tomorrow. Okay. Take care, guys. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.